Huffman coding is an algorithm used to encode data. It's used for things like image and file compression in JPEG and ZIP formats. As an example, let's imagine we want to send the character string A, B, A, B, A, C, D over a network. This data will be encoded in binary as zeros and ones. For example, in ASCII character, the character A, B, C, and D are encoded as shown in the diagram. In ASCII, one character is expressed with 8 bits. Using ASCII, we encoded the character string A, B, B, C, D. It resulted in a data size of 64 bits. In order to minimize network traffic, let's consider encoding the 64-bit character string into something smaller. In order to distinguish and handle a large number of characters, ASCII expresses one character with 8 bits. However, only 4 characters are used in the string A, B, B, C, D. It seems that we should encode these 4 characters in a distinguishable way. As a simple example, we come up with the encoding rule in the diagram. One character is expressed with 2 bits. We try encoding A, B, B, C, D according to our rules. It resulted in a data size of 16 bits, which is quite a reduction. Of course, because they are rules we just made up, we'll need to communicate the encoding rules to the side receiving the character string. For convenience, in this explanation we will ignore how much network traffic it takes to transmit the encoding rules. In order for the side receiving the character string to decode it, if they divide the code into 2 character segments and decode it by checking each segment against the rules, the original string A, B, B, C, D can be extracted. Let's consider encoding the same character to be even smaller with the earlier rules. We can able to express one character with 2 bits, but it seems that by expressing A and B with 1 bit, we can encode them to be even smaller. Furthermore, in the character string A, B, B, C, D, the characters A and B are used more than the characters C and D. Therefore, it seems like it would be better to express A and B with 1 bit rather than C and D. Anyway, we try encoding A, B, B, C, D according to the rules. It resulted in a data sizes of 10 bits, which is even more of a reduction. In order for the side receiving the code to decode it into a character string, each character should be checked against the conversion rules and decoded. But the code 10, for example, can express either BA or C. Due to this, a different character string 10 is extracted. These are the various other character strings that can be extracted as well, and the original character cannot be unambiguously determined. When the original characters cannot be unambiguously determined from code, it is called not uniquely decodable. Let's consider another example for our convenience. Let's assume that the 2 characters A and B will be encoded, as in the diagram. Let's consider the steps for decoding the code 0, 0, 0, 0, 0, 1 according to these encoding rules. When decoding, we look at the numbers in order from the beginning. The first number is 0, but we can't determine whether this stands for an A or part of A, B. The first 2 numbers are 0, 0, but we can't determine whether these stand for A or part of a B. The first 3 numbers are 0, 0, 0, but again we can't determine whether these stand for A or part of a B. Likewise, we can't make a determination with the first 4 numbers, nor with the first 5 numbers. Finally, we see the last number, 1, and determine that the first 0 is an A, and that the 00001 following it stands for B. We can unambiguously decode the numbers 0000001 into the character string A, B. At this point, there is no issue. Codes in a conversion table whose original characters can be determined as soon as they appear, which is called as instantaneous codes. But, as in above example, those whose characters cannot be determined without checking later characters are not an instantaneous codes. Thus, decoding takes some time. For the sake of efficient decoding, codes that are uniquely decodable and instantaneous codes are preferred. Let's consider where the problems lay in the 2 encoding rules used as examples. If we try to visualize the first set of encoding rules, if the first character in the given code is 0, we determine that it's an A. However, if it's a 1, it could be a B, or possibly part of a C or D. Let's try visualizing the second set of encoding rules in the previous way. Given any code, the first character can only be 0. However, that 0 could be A, or a part of B. In order for something to be uniquely decodable and instantaneous codes, there has to be the condition that no code will be part of the beginning of another code. The previous two examples did not meet that condition. Huffman coding is an algorithm that easily guides us to codes that are uniquely decodable and instantaneous codes. We will see the actual working example in the next video.